In this video, we're going to look at error estimates for trapezoidal and midpoint rule. That is, we're looking for an upper bound on the error of approximation. Let's assume that the absolute value of f double prime of x is less than or equal to k for x between, in the interval a to b. So k is a maximum of the second derivative of the function on the interval a to b. Error trapezoidal and error midpoint are defined as an upper bound of the error of trapezoidal rule and the midpoint rule. So the error trapezoidal is going to be absolute value of the definite integral a to b f of x dx minus trapezoidal rule approximation, and this is less than or equal to k times b minus a to the power of 3 divided by 12n squared. And for the midpoint rule, the upper bound of the error estimate is k times b minus a cubed divided by 24n squared. If you look at these two error estimate, they look almost identical. The only difference is for the trapezoidal error approximation, you're dividing by 12, and for the midpoint error estimate, you're dividing by 24. That means the midpoint error estimate is half the error estimate for trapezoidal rule, and that means the midpoint rule is more accurate, of course, because it has less error. The error is half of the trapezoidal rule. So the key concept is k is a maximum of the second derivative of the function, and finding k can be a little bit tricky. That's because the other parts, finding a and b and the number of intervals, that's pretty easy, but finding k can be hard. All right, so what we have is, let's look at an example. Here we have applied trapezoidal rule and midpoint rule with n equals 4 to estimate the integral, the definite integral 1 to 2, 1 over x dx. For part B, we're going to estimate the error bound. That means find an upper bound on the error and compare the exact error, or I should say the actual error, by applying fundamental theorem of calculus. So what we have is f of x is equal to 1 over x, that is the integrand. We have n is equal to 4. Delta x is equal to b minus a over n, that's 2 minus 1 over 4, because we know a is equal to 1, that's a lower limit of integration, and b is equal to 2. And delta x is going to be 2 minus 1 over 4, that's 0.25. So for the trapezoidal rule approximation, integral from 1 to 2, 1 over x dx. This is approximately equal to t4. That's delta x, 0.25, divided by 2, times f of 1 plus 2, f of 1.25, plus 2, f of 1.5, plus 2, f of 1.75, plus f of 2. So T4 is going to be 0.25 divided by 2. F of 1 is just 1 over 1. Plus 2 times f of 1.25. Well, f of x is 1 over x. So that's just going to be 1 over 1.25. Plus 2 times f of 1.5. That's 1 over 1.5. Plus 2 times 1 over 1.75, and f of 2 is going to be 1 over 2. If we simplify this, it comes out to 0.69702. That's the trapezoidal rule approximation with 4 trapezoids. All right, now let's do the midpoint rule. The function is the same. F of x is equal to 1 over x. N is equal to 4. Delta x is equal to b minus a over n, 2 minus 1 over 4. That's 0.25. Now, when you're doing the midpoint rule, you have to average these endpoints. So average a left-hand point and right-hand point, 1 plus 1.25 divided by 2, and you get the midpoint of every interval. Then you evaluate the function at the midpoint. Similarly, average these two endpoints, and you get 1.375. Average these two x values, you get 1.625. Average 1.75 and 2, and you get 1.875. All right, so we have the definite integral 1 to 2, 1 over x dx. This is equal to m4. It's approximately equal to m4. That's delta x, 0.25, times the functional value at the midpoint, 1.125, plus f of 1.375, plus f of 1.625, plus f of 1.875. Okay, let's calculate these. M4 is equal to 0.25 times the functional value, f of x is just 1 over x. That's going to be 1 over 1.125 plus 1 over 1.375, because f of x is 1 over x, plus 1 over 1.625, plus 1 over 1.875, and if we put this into a calculator, we will get 0.69122. So let's review this. We did a trapezoidal rule approximation to the definite integral, to this integral 1 to 2, 1 over x dx, and this came out to 0.69702. The midpoint approximation came out to 0.69122. And both of these are approximating the definite integral 1 to 2, 1 over x dx. All right, so let's look at for part B. For part B, the error estimate for the trapezoidal rule and the midpoint rule are given by these formulas. So our goal is to find k. K is the maximum of the second derivative on the interval from 1 to 2. And let's start with the function. F of x is equal to 1 over x. Let's differentiate this function. We get f prime of x. F prime of x is equal to, well, we can write 1 over x as x to the minus 1, apply the power rule, we get minus 1, x to the minus 2. So when we simplify, we get negative 1 over x squared, or minus x to the minus 2. They're both the same. Now differentiate again, and we get f double prime of x is equal to, apply the power rule, we get minus times minus 2, we get 2, x to the minus 3, which can be written as 2 over x cubed. Now, it's clear that the second derivative, f double prime of x, is equal to 2 over x cubed, is strictly decreasing on the interval 1 to 2, and therefore the absolute value of the second derivative would be less than or equal to 2. It would be less than this amount on the interval 1 to 2. So this is a very important concept. We're looking for k, which is a maximum of the second derivative of function. It's really a y value. It's not an x value. It happens that x equals 1, but we're looking for the y value. So since f double prime of x is equal to 2 over x cubed, is strictly decreasing on the x interval 1 to 2, the maximum value of the second derivative is achieved at the left endpoint. The left endpoint at x equals 1, and this value, f double prime of 1, is equal to 2. This is our k value. K is equal to 2. All right, so what we have is, for both trapezoidal rule and midpoint rule, k is equal to 2, a is 1, b is equal to 2, n is equal to 4. So let's do some computations. Let's find the upper bound for the trapezoidal rule and the upper bound of the error for trapezoidal rule and the midpoint rule. Error trapezoidal is going to be less than or equal to k, which is k is 2 times b minus a, that's 2 minus 1, all cubed, divided by 12 times n, which is 4, all squared. This comes out to 0.01042. This is an upper bound for the error of estimation for the trapezoidal rule. Now let's do the same for the midpoint rule. Error midpoint is less than or equal to k, which is 2, times b minus a, 2 minus 1 cubed, divided by 12 times, no, sorry, it's 24. For the midpoint rule, we divide by 24 times 4 squared. And this comes out to 0.00521. Notice how the upper bound for the midpoint rule is half the upper bound for the trapezoidal rule. So now let's apply the fundamental theorem of calculus to compute the actual error. So the integral from 1 to 2, 1 over x dx, we can integrate this. Integral of 1 over x is log x. Apply the fundamental theorem of calculus. So the upper limit is 2, the lower limit is 1. Plug in the upper limit, we get ln 2. Plug in the lower limit, we get ln 1. Log of 1 is 0. So the answer is log 2. And that this is approximately 0.69315. All right, so now let's compare the exact error and the error estimate for both the trapezoidal rule and the midpoint rule. Error trapezoidal, exact. This is going to be equal to absolute value, integral from 1 to 2, 1 over x dx, minus t4. And this is going to be 0.69315, which we found by applying the fundamental theorem of calculus, minus the trapezoidal rule approximation, which we found earlier to be 0.69702. The error trapezoidal exact, the actual error, is going to be approximately minus 0.00387. Let's take the absolute value, and we get 0.00387. Now for the midpoint rule, error midpoint, exact. This is going to be the integral from 1 to 2, 1 over x dx, minus m4, and this is going to be 0.69315 minus 0.69122, which we found was the midpoint approximation with 4 rectangles. So the error midpoint exact is going to be 0.00193. That's the difference of these two numbers if we put that into a calculator. So from the error estimate formula we found earlier, error trapezoidal was less than, the upper bound on the error was 0.01042. For the midpoint rule, error midpoint is less than or equal to 0.00521. Now compare the upper bound on the error for the trapezoidal rule, compare this number 0.01042 to the actual error, which is 0.00387, and you'll see how the upper bound is more than the actual error, as it should be. And similarly, for the midpoint error estimate, we have 0.00521, compare that to the actual error, which is 0.00193. So in both cases, the error estimates are larger than actual error computed by applying fundamental theorem of calculus, and this is why we call this an upper bound estimate for the error of approximation. So that's the reason we call it an upper bound. All right, thanks.